I am so excited today to be with my friend Patrick Rennie, rocket scientist, president of the Mars Society, board member of the British Interplanetary Society, and Patrick and I have been working for a few years on a lot of Mars Society stuff, mostly involving astronaut visits to the UK and student outreach, and just inspiring young people to dream big when it comes to not only going to Mars and the moon and all that, but studying rocket science in the first place and being involved with building a very exciting future. Patrick, thanks so much for joining me today.
Good morning, Sam. Thanks for hosting. It's a pleasure to be here.
I know your time is precious. You've got rockets to launch and engines to build and things like that. But could you tell me a little bit about how you got into rocket science?
Yeah, sure. So I was always interested in space and, the standard. You look out at the stars and see the night sky and it's all beautiful and everything and think, is this it? Are we really just here? Or can we go and do something a bit more exciting? More standard stuff like watching science fiction shows. Everybody loves Star Wars, but certain video games as well that inspired me. And so I knew I just wanted to keep doors open. As I was studying in school, I wanted to make sure that nothing was going to stop me from doing something interesting. So I tried to keep everything as broad as possible, and that led to me studying physics at university, which is the broadest sort of STEM subject that I could think of, because a physicist can go and do almost anything in the sort of technical disciplines. So I could have gone directly into physics research and astronomy, or I could have gone and worked in a bank doing mathematics. I could have done anything a mathematician could do, anything an engineer can do, as proven. I mean, I've gone and worked in aerospace. So after doing my degree, I wanted to keep doors open and sort of looked around for good graduate schemes, and ended up actually joining a large defense company, which I wasn't particularly fond of at the time, but it kept variety in my life, and I wasn't there for very long, until I saw that this particular company came along in Oxfordshire called Reaction Engines. And I saw it, and I immediately said to myself and my line manager, I'm going there. And I did everything I could, begged, borrowed, to go and do a placement. And so the host company I worked for sponsored me to go to Reaction Engines for a short placement. And
That's
then
amazing.
I basically never left. I said, I want to stay here. And yeah, so then I got into this company, and I was there for about 7.5 years working on space planes and air-breathing engines for space access, and it was the most exciting possible job anyone could have. I think I was one of the only people in the entire country that got to say that I could work on spaceplane concepts, working for the European Space Agency, UK Space Agency. We were doing design studies for what their applications were, looking at in-space manufacturing, for example. I met somebody, we looked at in situ resource utilization, sometimes shortened to ISRU, and looking at manufacturing stuff on the moon or in space and building big structures. And I fell in love with it. There was no way I was going to leave that. I stuck around until the company actually wound up a few months ago, about 6 months ago now.
Yeah, really tragic.
And tried to keep the flame alive. So it was a great shame that the company collapsed, but the people were the most phenomenal people I've ever worked with, and so motivated that we're trying to keep that dream alive. So what's important is that we weren't given up on as a technical concept, and I've carried some of that forward with me into my new job.
Yeah, I already have like 100,000 questions just off the back of what you've said there. But I'd be interested to know, first of all, how much of your work was practical and how much was conceptual. Like how much of what you were designing and working on made it to space?
None of that audio came through. I can see you speaking on your camera, but nothing's coming in.
Oh, damn it. Microphone.
Okay, now I can hear you again.
Now you can hear me. So I already have 100 questions off the back of what you just said. How much of your work was practical and how much was conceptual? Like, how much of what you did made it to space, or how much of it was sort of doing a lot of the brain stuff for the European Space Agency or the UK Space Agency or other suppliers?
Sure, sure. So in reality, I mean, we were looking at a concept that was a decade or more away from actually flying. So I didn't do any direct practical work. Like, you wouldn't find me with a welding torch or spanners and nuts and bolts. But we did a fair amount of design work that got to a decent level. So European Space Agency works to a systems engineering practice, and all of the standards are available online. You can find them. It's called the ECSS, and yeah, we got to preliminary design stage with the whole engine concept. So quite far down the line, actually, that we reached. So yeah, my time was spent on the conceptual side, which is a lot of fun, I must admit.
Yeah, I can imagine.
You get to really like blank canvas it, and try to determine where you're going. But with that said, we did do other projects that were smaller in scope and therefore further along in the design life cycle. So yeah, managed to do. We did actually build, or were part of a project that built hardware for, actually it was in space manufacturing. So as the space company in this consortium, the project was called SMARTER, which was space-based manufacturing, assembly and repair technology, exploration and realization. Something very close
Wow.
to that. It's been a while. Yeah, king of acronyms. And we did that project, and as a team, as a consortium, we built, using like robotic arms, an assembly facility that would attach these sort of hexagonal panels together in a space relevant environment, that had almost like radar, so antenna on them, so that we could demonstrate the feasibility of things like actually connecting electronically. And yeah, there was a big AI element to it too, machine learning, where you'd be able to recognize which panel you're picking up and attach it in the right orientation and everything like that. So we did build stuff as a company as well. I mean, the actual concept we worked on, so the propulsion side, got to backtrack a little bit here. We're talking space and fun and launching. We didn't build a space plane that can go to space, because that's a 10 billion plus program, 10 billion
Yep.
pounds program. And the UK Space Agency doesn't have that kind of budget to just sort of go, yeah, let's give it a go. So we what we were looking at was, what's the best way to go to space and back? At the moment, rockets are really unreliable. Even the best ones now, you're still having a failure maybe 1 in 100 times. And it's not really changed over the last 100, well, not 100 years, over the last sort of 50 years. Rocket launches are still of that order of magnitude unreliable. Now, bear in mind, a plane is 3 or 4 orders of magnitude more reliable than that. You wouldn't get on a plane and expect a 1 in 100 chance of not making it to the other side. So rockets are unreliable, and 50%, more than 50% of all failures are in the propulsion system, which means that if you rely on your propulsion for a safe landing, which is what even vertical reusable launchers do of today, then you're still running that same risk. Maybe
Yes.
you've eaten half of the reliability issues, but your propulsion is still going to cost you. Wings and wheels are passive safety systems. Planes can land without engines. And this is a famous thing. It's all scary. You look on the news, and there are, incidences where you could. I'd encourage anyone to Google some of the Boeing 777 flights where an engine was on fire, and there is a person like taking pictures of it on their phone from the window. But they made it home. They landed and then went home. So wings and wheels are a really good way of getting to space, which is why we were investigating it. But to afford the wings and wheels, which are heavy, you need more efficient propulsion. And that was the entire project that I was working on at Reaction Engines and actually carried forward to today.
Well, what an
So
amazing
it hasn't been to
project.
space
Yeah,
yet.
but I mean, what a great thing to get up and in the morning and go to work on. I mean, that's a really cool way to live your life. I know I'm biased, but I got to ask, space planes. People always think of the shuttle,
Yeah.
and so my big question with the shuttle, I know I've seen conceptual stuff about the Dream Chaser, but I don't know a huge amount about it. Is that Sierra Aerospace?
Sierra Nevada. Well, it's
Yeah,
now
just
just
Sierra Nevada.
yeah, I think it's now just Sierra. I can't remember, but yeah, you're
Yeah.
right. I remember the Dream Chaser concept. The idea of these space planes. So I'll tackle Dream Chaser first, and then the shuttle. Dream Chaser is a payload. It's a space plane, but only on the way home,
Yeah.
which means that as a payload on a rocket, you're just reliant on the rocket to get to space. It doesn't
Yeah.
have onboard propulsion. So the Dream Chaser will come home again and land just like the shuttle did, but it
Mm.
doesn't have its own engines, and it relies on the taxi service to space
Right.
first. So it's demonstrating how good wings are for coming home, but it's not demonstrating, it's not giving you any abort cases on the way up to space. The space shuttle did have that. It never needed it, which is a good and bad thing. People remember the space shuttle. It's one of my favorite space planes. Well, it's one of my favorite vehicles of all time. It's
Yeah.
amazing. Um, People always remember the two disasters.
Yeah.
Bear in mind there was over 150 flights, but so the
I think
reliability
it was
was about the same.
135 in the end.
Oh, thank you.
Yeah.
135. Yeah, yeah. So, people remember those two disasters, but that's actually on par with modern rockets in terms of
Yeah.
its reliability. And these two failures, each one never happened again. This is the thing with when you demonstrate planes, you fly a plane and you shake it down. You do a shakedown mission, which is where you fly it, you test it, you push it to its limits, and you discover every bit of it that is going to fail early. And reliability has what's typically known as the bathtub curve. And what you have is at the beginning of your flight, or the beginning of your life, you've got a lot of failures that are what you might call burn-in failures, things that you expect. Sometimes they call it, an early mortality, where components you test them and for some manufacturing defect, for some other reason, they fail, but they fail early. And the aircraft shakedown picks all of those faults up, and you replace those components, and then you enter the bottom of the bathtub curve, which is a flat reliability rate. It's we know what we've got, and once in a million it'll fail, and then as you reach the end of life it starts picking up again because components age and wear. With rockets and the space shuttle, it's all over on that left hand side. It's all over the early failures, because every flight is the first time you're testing something. Every time you fly one of these engines, you've refurbished it to a point where it's almost brand new. Solid rocket boosters, every single flight, they were reusable, but about 80% of it was rebuilt every flight. So it's like difficult to get to the bottom of that bathtub curve of reliability. So the space shuttle had and never needed these really cool abort modes where you take off. And the space shuttle is amazing because it sort of flies upside down, right? It banks round and then it's upside down as it ascends to space. But if something goes wrong on the way up, and it wasn't, the one disaster that they did have on the way up that was explosive in its nature, the space shuttle would detach from everything else, turn around, and then land somewhere downrange. So in Spain, they had landing sites specifically set up for the space shuttle, so that if something went wrong, they could just land. It's a blessing and a curse that we never saw that, because it would have demonstrated how good wings are at just keeping everyone safe. Unfortunately, the way it went wrong was with a rocket, with the O-rings in the solid rocket booster. So, we never got to see the space shuttle do the thing that it was meant to do, which is a great shame. But yeah, so the space shuttle's the same. The issue with it, compared to like the modern concept of a space plane, is that the space shuttle had all these bits around it, solid rocket boosters providing most of the thrust on takeoff, and then the giant external tank that it was attached to. So people said it was a 1.5 or 2.5 stage to orbit concept, because you had to have the solid rocket boosters come off, and then the external tank would separate off as the orbiter itself got to space. Whereas I'd say the ultimate concept of a space plane is you just take off from a runway, go to space, and come back again. No changing anything, no dropping bits off of it. If you want ultimate reusability and reliability, then it's one thing that goes to space and back.
Well, obviously that's never been done before. How I have so many questions about its feasibility, but
Yes.
could you just outline firstly how you could do that, how you could possibly have the propulsion on a space plane to just launch from a runway and make it to space, but also the getting back, because the big thing with the shuttle was the thermal tiles. I was actually very, very lucky last month. I got to talk to astronaut Steve Robinson. He flew on the return to flight after the Columbia disaster in 2005. And he did a very famous EVA where he was on the shuttle's robotic arm. He was maneuvered under the shuttle to basically do tummy surgery on it and remove some gap filler. It's an amazing story. I'm writing an article about it for Quest. But it's the tiles. I'm looking forward to finishing it. It's the tiles, the heat protection for something as complex in shape as a plane. You can't just drop back to Earth have all the thermal protection just burn off like the Apollo and Gemini sort of things.
Yeah, that's right. Yeah, I'm glad you raised this, because it was an important feature of the design that we had. First things first, wings and wheels, I said, are expensive, and you need more efficient propulsion to afford them. The reason the space shuttle had all of the extra stages was because the propulsion, despite being the best ISP of any rocket ever made, I think, any conventional one anyway, it was hydrogen and oxygen, which is the most efficient conventional fuel. There are some weird and wacky things out there that can do better, but at some substantial cost. So hydrogen and oxygen are really, really good together, and that had an ISP, a specific impulse of 465 seconds or something like that, something really, really extremely high, but still not good enough to buy yourself all of the extra weight needed for wings and wheels. Rockets are way less efficient than typical gas turbine engines, jet engines, which is why in our spaceplane concept, you use the air that you're flying through as your oxidizer. So one of the ironies of rockets is that the majority of any rocket ever carried on board is just oxygen. Liquid oxygen is more than half of the weight of any rocket ever made. And the irony is you're using that oxygen to push through this atmosphere that has oxygen in it. So air breathing engines, they trade this off and they become more efficient because you are swallowing the air as you're passing through it and using that to burn with your fuel instead of the cryogenic liquid oxygen that would otherwise be carried on board. So the company I worked for, and we're still investigating this now, if you have an air breathing engine that can go fast, then you can bite off a bunch of the mission, a bunch of the flight to orbit with a really, really efficient engine. And what that does is change how much you can carry to space for a given takeoff weight. It's called your mass fraction. And the famous equation called the rocket equation, or 𝐂onnect equation, tells you that for a given efficiency, you have a mass fraction for an amount of energy that you need so your mission energy, which we typically call delta V. So the change in speed you need to be where you are to flying around around the Earth. You know, for low Earth orbit, is somewhere like 8 kilometers a second. And to achieve that change in speed, you would burn an amount of fuel, or you would use of the object that you're sending. You would take a percentage of it as burnt fuel with a specific efficiency, or sometimes it's ISP, specific impulse, or exhaust velocity. They're largely interchangeable, just with the gravitational acceleration coefficient. And with even the best rockets, a single stage would need something like 93% fuel, something like that. I can't remember the exact number. It's very easy to work out. That's just not possible to build. You can't build something that's 7% structure and gets you to space with wings and wheels.
No.
So, you know, shifting it over, if you have this more efficient engine, higher exhaust velocity or specific impulse, then you end up with maybe 20%. And with 20%, you can start to afford these wings and wheels. So yeah, we were looking at that efficient propulsion where you're breathing in the atmosphere rather than carrying on board oxygen. Just one last bit on this is how fast you need to be going. So some launch concepts use a plane to start with, and typically we'll refer to this as a 0 stage rather than first stage, because it's a flying platform that carries you to a place on the planet at subsonic speed. So Mach 0.85 is the typical speed of a cruiser, of an airliner, and it will carry you to 10 kilometers, 11 kilometers altitude. Bear in mind, space is over 100, so it's not very high up compared to where space is, and it's not very fast. You know, Mach 1 is 343 meters a second, and you're doing Mach 0.85, so you're doing 300-ish meters a second out of 8 kilometers, so 8,000 meters a second mission speed. So a typical plane just doesn't buy you a substantial amount of the mission, which means that every single one, so there's Pegasus and there was Virgin Orbit, and they would drop off and they'd have 3 stages of rockets still left to go to take anything to space. So yeah, you need efficient propulsion, but for a good portion of the flight. So yeah, the one we were looking at was Mach 5. So 5 times the speed of sound, about 1,500 meters a second. So some measurable amount of the whole mission taken up with a specific impulse more than 10 times that of a rocket, and that just about gives you enough mass fraction with, you know, the world's best technology, with all of the developments that you'd expect over another decade or so to build this thing. You should get away with having a single plane that goes to space and back. Moving on to the second bit of your question,
the thermal
you were
protection
talking about coming home.
Yeah,
exactly. So the good thing about this particular concept was that it was using hydrogen as the fuel. So I said before, hydrogen and oxygen are the best propellant combination you can get. Hydrogen is extremely energetic. It is 3 times more energy per kilogram than diesel or kerosene jet A fuel. Like, it's very, very energetic, which is really good. So it's efficient for burning, but also everyone knows it's really, really light. So not dense, which means that you end up with what looks like a balloon. If you have a space plane that carries loads of hydrogen on it, you end up with almost like a dirigible, a blimp style aircraft. So what's called the ballistic coefficient. So this is sort of your volume versus your surface area, and it's your coefficient of drag. I'd encourage anyone to look up ballistic coefficient. This is what actually determines things like your terminal velocity and like heating rates and everything with re-entry. If you've got a really voluminous plane with also big wings, so big area coming in, and it's not very heavy, so ballistic coefficient is very important. It takes into account the mass of your object. If it's very lightweight and very large, then your ballistic coefficient is very favorable coming home again. Space shuttle was like a brick. It was amazing. Like I'd encourage anyone to read if you like a good book on the space shuttle. It's called Into the Black. I won't make an endorsement, but it's a very good book. And they talk about the flight characteristics of this brick. Diddy little wings, really high landing speeds. Trying to manage the energy with these S-bends coming home. So it was really, really hot as it came in. It came in fast, whereas a big blimp comes in really slow. And this was actually proven by SpaceX when they did the Starship landings, Starship re-entry. Giant, just because of how big it is and how much fuel they've used, and it's all empty, so it's really, really lightweight. As it comes in, they actually have a problem coming in because it just sort of wants to skip across the atmosphere.
Yes, I was going to ask about that.
Really low thermal. Yeah, really low thermal rates because of the sheer size of it. So specifically.
Yeah. Why doesn't it just bounce off the atmosphere? How does it get through?
Good question. I'm not an aerodynamicist, so I won't want to embarrass myself too much with the answer. But in short, it would always eventually come back in. It's an energy balance between like skipping a stone across water. The stone will always fall in eventually once enough energy has dissipated from it. I suppose would encourage anyone to do their own research on that because I'm not an expert on aerodynamics.
No worries. It struck me just that the thermal tiles were always a hazardous problem with the shuttle, and yet if you're going to have a plane design, you can't really do the Apollo Gemini thing of just cover it in this thermal stuff. It will burn off as it comes in. But then I think Apollo 10, held the record for the hottest return. It was like 25,000 miles an hour. And I guess just with the space plane design, there's no way you could return at really like that super high velocity, could you? Or can you?
No, and so you wouldn't. Well, ultimately, your speed is determined by your orbit. So when I said 8 kilometers a second or so, everyone says the quote space shuttle went 17,500 miles an hour, right? And it's just what is your orbital speed? So it's based on your altitude, and actually as you come in closer to Earth, if you've got an orbit that's closer, your speed is higher. It's more about how long you take to do it. So your thermal environment on re-entry is actually it's managing the energy. So you have this amount of energy. You're traveling at this speed around the Earth, and you need to eventually stop. So you've got this delta energy. Heating is power. So energy per unit time, which means that if you can take your time coming in, your heating rate goes down. So with the Apollo, I'm assuming this particular flight, they just came in hard. They're really fast.
They were coming back from the moon in a straight line.
Yeah, indeed. So with a space plane, what you would do instead, if you can control it, which typically, so you have like thrusters on the outside that will give you some altitude control and such. You would make sure that your entry condition is shallow, which means that you're spending a long time in the upper portion of the atmosphere. You're slowing down slowly, so you're reducing that heating rate. You still come home, but it'll just take a bit longer and be less aggressive of an environment. And that's also what that ballistic coefficient does in the first place. You're coming in slower. You're taking longer in the upper portion of the atmosphere. There's no sort of brick wall scenario here. Like the atmosphere is continuously varying with altitude. So if you can tailor it to be less aggressive, then you'll have an easier time. And you can do it with more conventional technology. And still, we just want to do the best we absolutely can and have carbon or ceramic matrix composite materials, all the fancy material stuff that again I'm not an expert on, but we know plenty of modern technologies that could be used, and we need to test them.
Well, we're all about polymaths here, and I find it remarkable with you because you're a physicist by training, but you got to work at the intersection of materials science, aerospace engineering. I mean, you have to be pretty versatile in the work you do, right?
Yeah, I have to dabble in a lot of things
Yeah.
to have an overall understanding, because when you deal with any of these vehicle concepts, it's just every bit. So I've said already on the call, I'm not an expert in aerodynamics, I'm not a material scientist, but I have to know enough about
Mm.
each bit to inform where we go with the
Yeah.
concept. Same with propulsion, performance, aerothermal. Yeah, lots of disciplines that I sort of meld together. My
Yeah.
actual job was systems architecture, they called it.
Yeah, you got to mix in a lot of chemistry there as well. But what's really encouraging about your story, I think, for students and particularly younger students, is you didn't go the master's and PhD route. You did a degree, and then you went into a graduate program, and yet you've had to train and absorb all these other bits of info, but you got to do it without the master's and PhD route, which I
Yeah.
think should encourage a lot of young people who sort of want to do physics and work in the space sector and stuff like that, but they want to get on with it and they don't want to have to stay in school for too long.
Yeah, I'd
um,
say the most important thing is to be curious. So
yeah.
I didn't even go to a particularly high-ranking university. In fact, I went to quite a low-ranking university, um, and only did a bachelor's degree, no master's, no PhD. And I just wanted to get out there, and because I was so curious, and I just wanted to
Mm.
see what the world had to offer. And I didn't want to sit in academia forever. I mean, it's interesting, and I could go, one day if I find something compelling enough, I might go and study it further. But I'd say, the quality of interest, the thing that gets you somewhere is this insatiable curiosity. If you're curious, then the rest will write itself.
Do you have any particular people that inspired you, or people that you saw either when you were young or along the way that really drove your interest to get into the work that you do?
Um, Weirdly, I would say that the person who had the biggest influence on me in terms of when I was young, when I was in early high school, or in early secondary school, um, was Sir David Attenborough. I used to love watching the nature documentaries and everything, and again, it's that curiosity. It's he'd explain something, and I think, how? Why is that way? Why is it like that? Um, yeah, there's a long list of names. I remember in school during chemistry reading about Dmitry Mendeleev and enjoying the periodic table and going, how did they work out? Why why are they grouped in that way? And they what?
Mm.
We just did experiments and found that things behaved in the same way, so we're going to put that one there, and then eventually found out about the atomic weight, and it just so happened to beautifully match up because science. Um, yeah, I um, yeah, across the board. I mean, through studying all of the big names, Niels Bohr, I had a particular
Mm.
fondness of his model of the atom because it made sense to me, rather than the sort of more modern, probability density cloud for an electron, which sort of blows my mind a bit. And quantum mechanics does me in, even though I say I'm a physicist, right? But even then, like I much prefer Newtonian stuff. Another example, like Newton. So Isaac Newton, not as a person, but the work that he did. Isaac Newton was so curious and interested that with the famous apple falling on his head situation and having to try to explain it, inventing a new type of calculus just to mathematically bound his theories was incredible.
Yeah.
And then my favorite is all thought experiments. Thought experiments are what sort of drove my curiosity and inspiration. It's when somebody just thinks about a problem and then come up with come up with an analogy or similar. So my favorite one that I explain to people, so space, everyone asks sort of, what if I was to ask a member of the public, how do you get to space? Most people that I've encountered would say you launch a rocket that way. So I always explain Newton's cannonball, which is an Isaac Newton thought experiment, which was you go up to the top of a really big hill and you fire a cannon, and the cannonball comes out and then falls to the ground. And Newton said, what if I fire it a bit faster? And the cannonball goes further and falls at a greater distance. And then you go further and faster and faster. And Newton was the one that came up with the concept of an orbit, because you fire that cannonball fast enough, and as the cannonball is falling back to Earth, the Earth is curving away from it. And that, in and of itself, was just the most beautiful, simple explanation of what an orbit is. It's nothing to do with how high up you are. It's everything to do with how fast you're going, so that you're in free fall around the Earth as the Earth is falling away from you. And so that, in terms of inspiration, thought experiments like that are my favorite. Einstein's thought experiment on special relativity, and I can't remember the names. There's always two names of people, and one's on a train that's traveling at this speed, and then they turn a torch on, and these kind of thought experiments are my favorite.
Yeah, I was talking yesterday to Professor Paul Ewart, who's Professor of Atomic and Laser Physics at Oxford. We were making the case, people, don't be scared of quantum physics. But it's a bit different for someone who has to do it as their job. I also think it's interesting, so many young people the world over will be saying David Attenborough is a massive inspiration to me in terms of curiosity and enjoying science. But I think it'd probably be a bit puzzled if you went up to him, shook his hand and said, you inspired me so much when I was a child, I became a rocket scientist. So
Indeed. Yeah, so for me it was the space shuttle, in that when it comes to the specific, so I was trying to cover like what made me curious. What gave me this weird mindset where I needed to move on and go through my degree, go broad. But then to go to space, specifically the space side, my inspirations were, this is kind of funny, but when I was really young, I had a model space shuttle hanging on my ceiling. And it was the coolest we had loads of planes on the ceiling, and the coolest one, the one that I always looked at, was the space shuttle, and that is probably the beginning of the space bug. And then over the course of the years, I mean, Star Wars is obviously like proper geeky. I'm very fond of science fiction, and I'd say the one that really blew my mind was actually a video game called Mass Effect. And the best bit about it was this game has like the explanations inside it. It's got an entire codex where you can read, and every concept, every bit of this universe was explained. Like a lot of games, a lot of books, they don't explain anything, and you just have to take as read, like it is this way because of this. The Mass Effect one in particular explained the Mass Effect. It was like at uni we learned about materials called multiferroics, which is like all of the interactions between fields. So you've got electromagnetism and gravity and mechanical force, and explaining materials that work across these things. So I'll get to gravity in a moment because that's the game. But electricity and magnetism, there are materials that, if you charge it, it will become magnetic, or if you magnetize it, it will exhibit like a potential difference. And we use these every day. So also piezoelectric, so a mechanical force on an object that will stimulate an electrical signal, or put electric current through an object and it will deform physically. We have that in quartz crystal watches. Every watch that anyone has a battery in is using piezoelectric materials to actually stimulate the timepiece, to deflect it and charge so at a known rate, and then it can tell the time. Mass Effect did that, but they said, if I put an electric charge through this thing, it's going to change the gravity field. And my mind was blown, and this game was like oh, this is how they travel faster than light, and then it opens the universe up, and this whole universe is just amazing and inspiring. And I want when when I got inspired, it was this: what can I do as a human? I've got my lifetime to work and contribute to society, have fun, whatever. What is what is the future I want to be a part of? What is the future I want to see? And come on, it's the science fiction future. I wanted to see like the expanse where we've got people on Mars and
Mm.
in the belt and all these kind of things. So yeah, and that got me to work in space because we can either live here and be on Earth, which is the most beautiful planet ever, but are we going to end up in the stars or are we going to end up just ending it here?
Yeah, I love that. Let's talk about deep space. I mean, with the
Okay.
time we have, because you're the president of the Mars Society, and I encourage people, if you've got interest in the space sector or if you're working in it, join the Mars Society, join the British Interplanetary Society, go to the conferences, go to the events. I mean, we've been very lucky the last couple of years. We had NASA Hall of Fame astronaut Michael Foale visit last year. We had NASA astronaut Tony Antonelli, who was heading up the human Mars side of things after he retired. It's a great thing to be a part of. But going to Mars, I mean, you can be as optimistic or pessimistic as you like. Just let it all hang out. How seriously should people take the possibility of us being on Mars anytime soon, and what do you think that will look like?
Okay. So first things first. Yes. I'm the president of the Mars Society in the UK. We've been fairly quiet since COVID actually, and we're just in this process now of trying to ramp back up. So watch this space, but in the near future, we will reopen membership. I think we're gonna completely change how we do it and make it so that it's more accessible to absolutely everyone. Because really, what matters is getting people talking
Yeah,
and interested and excited for the future. We've got so much going on in the world today that it's easy to get sort of down in the dumps and feel like everything's bleak. But what I want to do at the Mars Society is get people talking about an exciting future. Um, so on that note, when will people land on Mars? Um, the number of times I've been asked that question uh, is large. I I couldn't say because I'm a bit of a cynic. I've worked in the space industry for 10 years and I know how hard it is. And a lot of people, you've got the Elon Musk timescale. We're going to get to Mars in a decade. You've got the Mars Society in the US that in 1990 said we could get to Mars in a decade. Yes, the answer is you could. It is physically possible. It is feasible, but it would have to be international, global effort. Everyone needs to agree, and we need to do this thing. So feasibly, people could land on Mars within a decade from now. I mean, less than that. Realistically, I'd say within, what year are we in? 25. By 2040, so within 15 years, I would be surprised if humans haven't set foot on Mars. I wouldn't say permanent settlement.
mm.
I would just be surprised if we haven't landed there within that sort of timescale. 2040 feels appropriate with the drive from characters like Elon Musk, the rise of heavy lift launch vehicles giving us the capability to be able to do it again. Because realistically, the United States had the capability to go to Mars with a substantial payload, that is, when Saturn V existed. Um, then obviously that got cancelled over after Apollo 17 and everything. So capability wise, yeah, I'd say I would expect to see boots on Mars by 2040, but probably small missions to start with.
Mm.
And I would encourage that because I think we need to do the science first. I think there's a lot on Mars that we
Yes.
haven't uncovered, and I've always joked about this. I'm probably the most uh, the least human-centric Mars Society president there's ever been. I would say I'm the least keen on just send everyone there, get boots on the ground, because I, want to be cautious and considered, and there's a lot of science to do, and I don't want to, get to Mars and then you're digging around and you go, we found life. Looks an awful lot like the microbial life on Earth. Was that us?
Yeah, probably.
Don't want to don't want to ruin it that way. You want to get there, do the science, and then expand sensibly, cautiously. After learning as much as we can first. Yeah. Was there a second part of your question? That's when we get to Mars.
Well, is it a question very much of will and access and money rather than technological? Because there's a sense. I mean, I work in DNA repair, and you just look at the levels of radiation on the surface of Mars and the atmosphere difference, and you think, how is anyone going to be able to live here for 5 minutes? But people are shocked to find that actually most of the technological stuff is accounted for. I mean, it's not impossible. It's certainly not impossible. So what do you think is going to be the challenge?
Oh goodness. I've given presentations on how much of a hellscape Mars is and how horrible it will be to live there, but that we should do it anyway because of the pioneering engineering, the pushing forward and discovery and everything. The challenges are substantial. There are many of them. So I like trying to go in order here. You've got the journey to Mars. This is hard, and at the moment, the best case scenario you're looking at is about 7 months, right? Everyone says if you were to do a minimum energy mission, so what's called like a home and transfer, on the best day of a 2-year period, it will take you 7 months to go to Mars if you've got an energetic rocket. So that's a long time to be sort of sat in deep space exposed, and the shielding requirement, an astronaut will take in a lot of radiation even just on the journey to Mars, let alone landing on the surface and being exposed to the solar radiation, because Mars doesn't have much of a magnetic field. The other bit is when you get there, you have to land, and Mars has a very, very, very thin atmosphere, extremely thin, less than 1% of the density of the Earth's atmosphere. And what that does is it means that your speed as you come in is way faster. So if you do the equation for like terminal velocity, which is based on like coefficient of drag, you've got gravitational acceleration, and then you've got the density of the atmosphere in there as well. When you resolve the equation for speed, if you put in the numbers for Mars, which is 38% gravity and I think it was 0.6% density, something like that, it resolves to about 5 times the speed. You're coming in 5 times faster, which is difficult. Yeah, like how do you slow down? You need to manage all of that energy because you've just done an interplanetary trajectory. The speed that you're traveling at is enormous, and you have to be traveling at more than 11 kilometers a second to leave Earth. And then you enter Mars's sphere of influence, and then you have to slow down. All of that energy has to go. And you've got this super thin atmosphere, so aerobraking, where you're using the atmosphere to try to slow you down, it's going to take too long, or it's too difficult. And so Elon Musk's propulsive landing is a fairly good idea, but that takes a lot of fuel, and like there's a lot of challenges involved with this. The heaviest thing that has ever been landed on Mars to date is 1 ton. As you get heavier, it gets harder to land, a lot harder. I mean, the terminal velocity I was just talking about, it scales very poorly. It's the equivalent, the 5 times speed is the same as being 25 times the mass if you were to drop something on Earth. So imagine, I tried to do an outreach experiment for children on this, and I'd encourage any teachers listening to give this a go. You do an egg drop challenge, right? It's classic. Everyone loves an egg drop challenge where you make something with a parachute or whatever, and then you land it and you make sure the egg doesn't break. If you were to do that in Earth's atmosphere, but to simulate Mars, make it 25 times heavier, and that is the same experience. That'll give you the 5 times the speed that you would have on Mars. And it's just like your egg is going to smash.
Yes.
It is going to smash. So the landing is really difficult. Then you get to the surface, and then you've got all the radiation problems as described. The best case is, oh, okay, we're going to go into a lava tube. But then you're in a cave.
Yeah.
Yeah, how much? So, yeah, the challenges are substantial, but everything could be resolved. I don't see a technical like showstopper for going to Mars. Even on the travel to Mars, you can get there faster. It is doable. I wouldn't recommend it with a chemical rocket. I would say the future of interplanetary propulsion is nuclear. There's just so much more energy involved, and maybe on another call I'll explain all about that, because I've dabbled in nuclear propulsion as well with projects from reaction engines and otherwise. So I can talk about that, but not with a few minutes left to go.
Yes, I did want to ask you about that, but we'll have to leave people wanting more, I think. Just for young people or older people who want to learn more about the space sector or get involved, what do you recommend?
So I don't want to come across biased. I'll declare that I sit on the council of the British Interplanetary Society. That's a good starting point. So there are a lot of groups, a lot of space advocacy groups across the nation and, in fact, across the world. Something fun about the British Interplanetary Society is that they're the oldest continually existing space advocacy group in the world. I think it's 1933 they founded, so way before the first rocket was ever launched. The British Interplanetary Society were looking at moon landings. Is amazing. So it's talk to people. If you're interested in doing it as a career, then I would say, I advocate for keeping your horizons broad. So I studied physics for that reason. Anyone who's younger, so if you're doing GCSEs, you're in luck, because you have to do physics and maths anyway. But for A levels, physics and maths are the gateway to STEM subjects. You cannot at university study anything sort of technical without having done physics and maths first, or actually, without wishing to scare anyone off, you can do what's called a foundation degree. It will just cost you an extra year to do that. So physics and maths are the first thing to open your technical horizons. It's the subjects to study that will keep you able to study engineering at university, maths, physics. And then I would say keeping it broad with work. I mean, if you want to work on this stuff, then do a wide degree and then join a wide grad scheme. There are plenty of space companies out there now. When I was leaving university 10 years ago, I needed to go into the world of defense, because it was the only thing I could see that was even slightly linked to space. There wasn't a lot going on. I could have joined. There was a space company local to me, one big one that's now Airbus. Otherwise, there just wasn't anything that I could find. Whereas modern, like in the last 10 years, things have gone amazing. There's campuses of space activity in Leicester, in Harwell. There's multiple space campuses across the nation. Find your local space campus and find out what they're doing. There's a swathe of companies in every single one doing anything from making stuff in space, active debris removal, which is amazing, and we're going to clean up the environment by picking up junk from space and chucking it back home and making it burn up instead of risking collisions and catastrophe in space. There's companies that do data communications, even something as exciting as space-based solar power, where we're going to send up giant effectively like mirrors that will concentrate power and then beam back down to Earth, and all of our energy generation will be in space, and then we no longer have these big fossil fuel burning power stations and so on. Like the horizon is limitless for space. So I'd recommend finding your local cluster, That's what they're typically called, space clusters. Look up the UK Space Agency. They'll have lots of resources out there to investigate space. European Space Agency, doesn't matter about Brexit, we are still members of the European Space Agency because they're not the European Union, so we're still members of 𝐬𝐁𝐒. Look them up. They've got lots of interesting things, from manufacturing bricks of moon regolith, that's like the dirt on the moon. They make bricks out of it to build habitats, all sorts of amazing things. I just recommend stay curious and look this stuff up. It's all out there to be found.
Amazing. Thank you so much, Patrick Rennie. We could talk for hours about this, and sometimes we have.
Indeed.
But no, it's just brilliant hearing from you, and I really hope people have been inspired and that they've become more curious about it too. And I look forward to catching up with you again soon.
Likewise. Thank you, Sam. It's been a pleasure.
Thank you very much.